Part C, the title, Role of Data Structures in Algorithms. In this part, in order to convey something important, that is the role of the data structures, I just use a very simple example. Later, we have one module, we talk about advanced data structures. In our module 5, we will talk about a few relatively more advanced data structures. All right. Topic C.1, search unordered arrays. This is a very simple problem, also a computing problem. Very simple, but I have several concepts, methods, still we have a lot of things to learn in this part, in this sub topic. Let me call it subtopic. All right, let's start. Our problem number 2, search an unordered array. First, let me give you the question first. Given an unordered array, we use this notation, array notation, capital A, bracket, square bracket, then indices from 0 through n-1. All right. Also, we are given a search key K. The question, find an index I such that K equals A of I. That's the basic search problem. Very simple, right? I believe everyone in this class knows how to solve it. But here we still, because we need to use this example to introduce several concepts, some basic methods, things like that. So we need to study it, all the details. All right, first, let's look at the category. The problem type of this one, it's the search type. We know it's a search problem, but why I talk about this, it's very simple. In this class, we will learn 3 basic types problems, 3 basic types. All right, so the first one, search type. Sorry, my spelling. Search type. Second, sort. And the third, selection problem. Selection problem, These 3 basic types, We will cover search type and selection type in our module 1. Then from module 2, and actually in several other many remaining modules, we need to do sort. We will do approximately 6 or 7 times on sorting problem. 6 or 7, that many for this class. So you can see how important the problem is. All right, that's the problem type. Data structure for this example, array. Most commonly used data structure, array, and the simplest, right? The simplest, almost the simplest. Let's say almost the simplest. All right. I'll give you the reference here on our textbook. All right, so let's start. Do the analysis. First, before we do the analysis, let me ask this question. Why the data structures are important in algorithm design? The answer is pretty simple and pretty straightforward. Actually, you can connect this answer to your real life experience. let me give you the answer, all right? Through the data structures, we can make our data well organized. This is a key word. Make our data well organized and take advantage of the structures for better performance. Yeah. So that's the answer. Yeah. Why? So here, for the understanding part, why the organized data will result in better performance. Okay, yeah. So this kind of thing, I like you to connect to your real life experience. Yeah. Think about that. If you arrange your everyday, your personal stuff in a well-organized way, right? Yeah, because we know for many of us, it is very hard to organize our stuff in a well-organized way. For myself, I have the same problem. Yeah, it's common. Yeah, but think about that. If someone can do that, organize your stuff in a very, super great, efficient way, you can imagine it is very easy to find your stuff when you need it. Okay, yeah, that's pretty simple. Yeah, all right. But here for our data, we have the same thing. If we organize in a super efficient data structure, then when we need one particular data item, we can find it quickly, right? So we can enjoy the result. Yeah. All right. Yeah. So, all right. So that's the first question. Yeah. Before we start our analysis. Yeah. All right. Analysis part. Yeah. To solve this problem, we need a basic operation. Yeah. Comparison. So this time, not addition, not multiplication. It is comparison. Yeah. All right. Basic comparison. But when we do comparison, so let's look at a typical comparison. Compare the key K, given key K, with one of the array elements, A of I. Initial value I equals 0. Yeah. Then the possibilities, 2 possibilities. Yeah. Yeah. You can say 3 possibilities, right? K less than or greater than, but here we combine less than, greater than as one case, not equal case, okay? Not equal case, equal case and not equal case, all right? 2 cases. If it is the equal case, then we have the answer, return I, that's it, okay? Yeah, we complete the solution, all right? Yeah, but not equal, then we need to do iterations. Yeah. For the iterations, we need to compare K and the next array element in the sequence. Yeah. K, A of I plus 1. Yeah. When you do comparison, you need to go back to, the cycle again, 2 cases, equal or not equal, yeah, again, all right, yeah. And eventually you may reach the end. Yeah. If you do not get an answer, but you hit the end, right? Yeah. You couldn't get the equal case. Let's say it in this way. You couldn't get the equal case all the way to the end. Then you have to return -1. This -1, you want to, tell the programmer, yeah, so I couldn't find the key in this array. Yeah. So that is the case. The key cannot be found in the array. We can still treat as a solution. Yeah. Although the key cannot be found, but you get a solution. Yeah. because the solution is the given key is not in the array. That's the solution. All right. All right. So that's the solution description, the whole solution description. All right. Yeah. And this algorithm, we're familiar with this algorithm. Yeah. It is called a sequential search. We search an element in the array. We search a key in the array in a sequential way. Yeah. Some people also call it linear search. Yeah. The same thing. Yeah. So we use these two different names, both in this class. Yeah. Sequential search or linear search in this class. Yeah. All right. Okay. After we complete, we need to do discussion. Yeah. The first thing, efficiency discussion. How efficient is this algorithm? Yeah. All right. So let's do analysis. To do, we need to count the number of comparisons. How many comparisons do we need to solve this problem? Yeah. All right. Here, I like to do a chart in this one because the given key could be any of the element in the array, and the last case, no match. Okay, that's all the possible cases, right? One of the elements in the array, the first n cases, and the last case, the n plus one, one more, no match case, couldn't be found. That's all the cases. So let's count the number of operations, this time comparisons, one by one. If k equals a of 0, one comparison, a of 1, two comparisons, and so on. All right. The last array element, n comparisons. All right. Then no match case, also n comparisons. So that's all the possibilities. All right. So now the question. After we collect all the data we need, let us do further discussion. The first thing is, what is the best case? One is the best case. The minimum number of comparisons you need to find a possible solution. It's possible, right? K equals a of 0. That is one of the possibilities for the solution. So that's the best case, one. And the worst case, the maximum number of comparisons you need to solve this problem, last two cases, not just one, last two cases, they need n comparisons. So that's the worst case. All right. Next, we want to find the overall efficiency. How to measure overall efficiency. Why you want to measure overall efficiency? Because when people ask you for the efficiency number for one algorithm, what is the best way to describe the efficiency of certain algorithm? What is the best way? The overall efficiency is the best way, right? Because not the best case. If you give the best case to describe the efficiency of one algorithm, it may not be fair, right? Because most other cases will generate worse numbers, right? So the best case not a fair description number, right? Also, for the worst case, if you give the worst case to other people to describe the efficiency, also not a fair one, right? because the most other cases, they will have better numbers, right? Yeah. So you should consider, you should factor in all the possible cases, and pretty much you need to take the average, right? You need to average all the possible cases. That's the overall efficiency. That's our average case efficiency. Yeah, not the best case, not the worst case. We need to use the average case efficiency to give the people who ask us about the overall efficiency. All right, yeah, so here, the question is, if we want to measure all the possible cases, the question is, how do we do the computation? How do we calculate it? How do we do the correct calculation to factor in all the possible cases? That's the main question. Yeah. All right. And usually it is not that easy. Yeah. In this class, I will give you many questions, ask you to calculate the average case efficiency. Yeah. Later you will see. Yeah. Not that easy, not that straightforward. Yeah. In arithmetics, you know how to do the average, right? How to calculate the average in arithmetics. Yeah. But here, our calculation, yeah, although we will also use the arithmetic way to do the calculation, but yeah, you will see we need to consider a lot of things carefully. Yeah. All right. Yeah. How do we know all the cases? Here, we list all the cases, right? Yeah. You see n+1 cases. That's all the cases. We know them, okay? The question is, how do we use those n numbers in a fair way, right? In a fair way. So here, yeah, we always talk about a fair way here. Yeah, we need to make assumptions. Yeah, for this question, we need to make another important assumption. Yeah. If we do not do that, probably we couldn't find the answer in a fair way. Yeah, so this assumption is very important. So let me use another slide to explain that assumption. Yeah, our topic C.2, average efficiency. Yeah, actually it should be average case efficiency. Yeah, yeah. I will update my title. Yeah, average case efficiency. Yeah. Let me write it better. Average case efficiency. All right. Yeah. First, let us do our assumption first. Yeah. What kind of assumption? Yeah. Here, think about this. Our given key K, there are two possibilities. One possibility is the K appears in the given array. The second possibility, the K does not appear in the given array, right? So these two possibilities. The question is, in what percentage, in what probability that K appears in the given array? Nobody knows that, right? What is the probability that K appears in the given array? Who knows that? Nobody has that information, right? Can you assume some reasonable number for it? Nobody can assume a reasonable number for it, right? Yeah. So for that reason, because nobody, yeah, is that smart, yeah, to find a correct number for that case, right? So we need to make assumption regarding this situation. Assume that these cases, that K appears in the array, that case, have all right. So actually here I go a little faster than I want to. So here, actually this assumption is our second assumption. This is the second assumption. All right. But we need to have the first assumption. Then we have the second assumption. All right. The first assumption is the probability assumption. Yes. Probability for the index case, the algorithm that returns some index from 0 through n-1. All right. So that's a valid index value. The function returns a valid index value. Then the -1 case, -1 is not a valid index, right? So it tells us a different meaning. The key does not exist in the array. Right? So we can make assumptions on these two cases. For the index case, we assume the probability is p value. The p-value should be between 0 and 1. The probability p-value between 0 and 1. Okay, But this p, nobody can tell us the exact p number, right? It has to be based on your real-world application. In the real-world application, this p could come from statistics. Right? The real-world statistics. Okay? Statistics based on history data. How about that? History data. Okay? So we have that p number. All right? We have that p number in our real-world application. All right. Then the -1 case, 1 minus p. The complementary case, right? 1 minus p. Under this assumption, this is our first assumption. Then we can get to our second assumption. Then among the first case, index case, there are n subcases, 1, 2, 3 through n subcases. For those n subcases, then we make our second assumption, assume that these cases have the same probability. Now, after these two assumptions, now we are ready to calculate the average case efficiency. So you can see this kind of preparation is important. Now, think about if you do not do the preparation like this. Let's say, suppose we do not do these two assumptions. People just do the calculation, calculate the average case. We know the definition of average of n+1 numbers, right? Plus n divided by n+1. Most people may calculate the average case efficiency using this formula, right? Without assumption. People may do it in this way. Is it a fair way? Right? If you do it in this way, is it a fair way? Right? Yes. Think about that. Now, because our answer should rely on P, right? Our answer should rely on P. And here in this expression, you do not use that P, right? Think about when the P value larger, smaller, you can change that P value, right? Then your answer should be different. When you change the P value, your answer should be different. But here, this answer does not rely on P. right? So you can imagine this first try, yeah, let's say if you make this as a first try, it may not be a good answer. Yeah, it may not be a good answer. All right, so let's continue to find the correct answer. That should rely on P, yeah, that answer. Yeah. All right, let us do analysis under these two assumptions. Yeah. All right. Let's look at the first subcase. In the first subcase and the second subcase, let's do average separately. What is the average efficiency for the first subcase? That means corresponds to those braces. All right, yeah, first subcase. Second subcase, only one case. All right, yeah. The first subcase, yeah, we can calculate the average in our usual way, in our normal way, adding up all n numbers, then take do the division by n, yeah, our normal way. Yeah. But the second subcase, that's only one single case. That's the same number. Yeah. You do not need to take another average. Yeah, here, yeah, we just treat this as, you know, the average for one case itself. Yeah. Now the question, next question, how do we combine these two cases? That's the question. How do we combine these two cases in a fair way, right? In a fair way, yeah. The first case, the corresponding probability is P. The second case, the corresponding probability is 1 minus P. Yeah, look at that. Yeah, with this information, can you imagine some fair way to put things together to get an overall average? That's what we need to do. The average should cover all the possibilities, but in a reasonable, in a fair way. That's what we need to do. Yeah, next. Yeah. All right. So next, the way we do it, weighted average way. Weighted average. Have you heard of this term, weighted average? When we take the average, we need to factor in the weight. All right. Let's look at this formula. It explains the meaning of the weighted average. First, this 1/2 parenthesis n plus 1, that's the average number for the first subcase. Then its probability, its corresponding probability P, we use it as the weight for the first case. Then for the second subcase, its average number is n, but its weight, 1 minus P, is its corresponding probability as the weight for the second subcase. Now, to combine these two subcases in a fair way, we multiply their corresponding weights as the coefficients of these two average case numbers. And the result, we treat it as the overall average case efficiency. How about that? How about this kind of computation? Think about, is this way to find the average fair or not, reasonable or not, right? Try to connect to your real world experience to understand if this way is reasonable or not, all right? Can you connect to your real world experience a little bit to understand this way for calculation? Yeah, a little bit, yeah. Here, let me imagine some real world situation. Yeah. For example, people do investment in the stock market. Yeah. Think about that. Here, let's assume there are two stocks, the first stock and the second stock, right? Yeah, real world experience. The first, because when people do investment, the share could be different, right? Yeah, the share, we know in your portfolio, yeah, the share could be different, the percentage different in your portfolio, right? This P, we just treat as the percentage, you know, the first stock, you know, P percent, right? Second, 1 minus P percent, right? The first one, the return, the earning return, yeah, this number. The second one, the return, that number. When you try to calculate your total return, do you do the weighted average, right? Yeah. So the right way, you do the weighted average, yeah, because you can feel about that number, right? Yeah, that's your investment. That's your final return, right? So you can feel about it in that situation, in the real world, your real world experience, real life experience. Yeah. So if you can connect the way we do the calculation at weighted average to your real life experience, then you can understand better. So then you will feel, oh, so this is the right way to calculate the overall average case efficiency. Yeah. All right. So that's this topic. Yeah. Any questions so far? Yeah. So we find the final answer. So this topic. So we complete this subtopic. Yeah. All right. Next, yeah, I like to talk about, if you do not have any questions, we move to the next topic. So I like, yeah. Oh, before next topic, I have one concept I need to introduce here before I move to the next topic. The dominant term concept. Yeah. So why dominant term? To look at this whole expression. Yeah, relatively complicated, right? Yeah, relatively complicated. Yeah. So we want some simplification. Yeah. We do not want to use this complicated expression. Yeah. So we want to use the simplest possible expression for it. Yeah. So in that situation, we try to find the dominant term. What is the dominant term? Yeah. Here, that plus one can be ignored, right? When we looking for a dominant term, that plus one term is not important. Yeah, not dominant, right? We only look at the dominant part. So the plus one, the minor part, can be ignored. Yeah. All right. So then you can see the first term. Yeah. So the answer is this one. The first term contribution, 1/2 and P, the first term contribution. The second term contribution, yeah, the second term, 1 minus P, we cannot ignore anything in this because this number needs to time and, yeah, so look at the 1/2 P plus 1 minus P, the coefficient part. Yeah. This number equals 1 minus 1/2 P. Yeah. So that's this parenthesis, inside big parenthesis number. Yeah. This we treat as, this number we treat as the dominant term. Yeah. Yeah. Because that big parenthesis, you need to multiply that variable n. Yeah. So that's the, you know, the most important term in our answer expression. Yeah. Yeah. All right. So later, we need to use this dominant term many times, especially in our module 2, we need to use this concept a lot. So here, that is just the introduction, the dominant term. Yeah. All right. Yeah. Then we move to our next topic. Actually, this is our last topic of today, the repeated squaring technique. It's a pretty smart technique. So this one's pretty smart. Okay, little tricky, smart technique. All right. But before I talk about this technique, I may like to talk about our programming project number 1 first. Yes. First, at this time, I can talk about our next assignment. All right. Now we're at a point for our first assignment this semester. Based on our timeline schedule, that diagram I gave you in first video. If you still remember that. At this point, we need to consider 2 possible assignments. One is quiz 1. Another is project 1. All right. So let me just arrange my laptop a little bit. All right. So I can get a good position right on the screen. All right. Let me just rewrite it. All right. These 2 assignments. The screen is very sensitive. Quiz 1 for module 1 and project 1. All right. But the quiz 1 should be at the end of module 1. After today's class, we have a very important topic, part D of module 1. Part D of module 1. In that part, I need to talk about a big important problem, optimality problem. Optimality problem. So I don't want to, exclude this important topic in quiz 1. So I want to wait for another class. After we complete another class, then I assign you quiz number 1. So that's the impact from our part B of module 1. We use 2 class sessions to cover part B, so we need to push back our quiz a few more days. But the good thing is we are ready to do project 1, right? So what I mean is in our timeline schedule, the coursework timeline schedule, we need to swap these 2 assignments. So we do project 1 first, then quiz 1 after project 1. Okay, so that means after today's class, I will assign you project number 1 first. So you will see project 1 description. Let me give you approximate time I do the assignment, today or tomorrow. Either late today or early tomorrow. These 2, so you approximate time I post this assignment. So I will create an assignment page. You will see an assignment page. Then I put this assignment link under module 1. Under the title of module 1, so you can find it easily from module 1 title. So that's project 1. Then quiz number 1. Quiz number 1. Yes, we met. Just a minute. Because for this class, algorithm class, we use Tuesday and Thursday to deliver the lecture, right? Yeah, Tuesday, Thursday, yeah. Then remember, this coming Monday is the Labor Day holiday, right? Labor Day holiday. There is no class on Labor Day holiday. But for this class, there is no impact from the Labor Day holiday, right? Yeah. So because our normal lecture delivery time is Tuesday after the Labor Day. Yeah. So we don't worry about if we lose one class or not. Yeah. So on Tuesday, we will complete the part D of module 1. Yeah. So that means on Wednesday, I can post quiz 1. Approximately Wednesday, I can post the quiz 1. Yeah. So that's appropriate, switching quiz 1 and project 1 on our original coursework timeline schedule. Yeah. So if you go back in that diagram, I put a project 1 approximately at a Wednesday. Yeah. Approximately at a Wednesday. So now we flip. Yeah. Quiz 1, project 1, we flip. Yeah. So we do this kind of adjustment. Yeah. Because for our special situation, so we try to follow closely to our original plan. Yeah. Try to follow the best we can. But in a situation like this, we do some minimum of adjustment. Yeah. Even when we do adjustment, we do minimum adjustment. Yeah. All right. Just let you know this kind of update. Yeah. All right. Then for project 1, let's go back to our project 1. I gave you some information last time about the project 1, right? Yeah. So let me just repeat that another time. For project 1, we need to do evaluation, or we need to calculate the value of a polynomial, given polynomial. Yeah. That polynomial, the degree is pretty high. Yeah, the degree, it's not like in your middle school. In your middle school time, you need to calculate the value of certain polynomial, right? But usually that kind of polynomial, the degree is very relatively small. Yeah, very small. So let me give you an idea. How high is the degree? I like to put in this project as high as n equals approximately 200,000. This high. In this category, 200,000. You calculate the polynomial value. We will generate this polynomial using random functions. We use random function to generate polynomial. Okay, yeah. Random function. How to use random function to generate? In my project description, I will tell you how to generate the rules. Yeah, I will describe the rules to generate polynomial. Yeah. All right. So after that, you have a big polynomial. You need to do the calculation now, because the reason I use such a high degree is it's too sensitive. Such a high degree. If I do not use this high degree, you won't see the big difference. We want to see the big difference among 3 methods, 3 different methods. Let me repeat that 3 methods again. The first one, the brute force method. That's just you calculate a polynomial directly. Yeah, so use your usual way to do the calculation. All right, brute force method. Yeah, the second. All right, yeah, second. Use the existing power function to calculate the monomials you know monomials, right? X to the kth power. This is a monomial. When you calculate x to the kth power, you just apply the existing power function. I will talk about the existing power function a little bit later. Now, I use Java to talk about it. Yeah. All right, yeah. So that's method number 2. Yeah. Method 3, Horner's rule. Yeah, Horner's rule. So that's what we learned in Module 1 Part B. Yeah, so you will do the comparison. You can see the huge difference. Yeah, method 1 extremely slow. Method 1 is extremely slow. How slow it is? Let me give you an idea, approximate, because different people, your computer, speed could be different, right? I cannot, guess your computer speed. Yeah, I just use my laptop. My laptop is, not very fast. Yeah, so, probably not as fast as the average computer. All right, in my laptop, to calculate n equals 200,000 approximately, using the brute force method, I need approximately 30 seconds. Can you imagine how slow 30 seconds? 30 seconds. Think about, yeah. In your real life experience, if you do something in 30 seconds, that's very fast. But if you are waiting for the response, you're waiting for the result of a computer, the response time is 30 seconds. That's extremely slow. You will feel about it. Yeah. So I intentionally let you do this kind of computation, let you feel about how slow it is for this 30 seconds. All right. Yeah. Then method 2, pretty fast. Method 3, extremely fast. All right. Extremely fast. Then you will get a big impression. Yeah, how big is the difference for an efficient algorithm and a slow algorithm? Yeah, you will appreciate the huge difference. All right. Yeah. So that's some basic information for the project. Yeah. All right. Next, about the existing power function, I use Java. In Java, the syntax. Yeah, look at the syntax for the power function. POW. Yeah, the name of the function, the method. Yeah, we call it method. POW. Yeah, 2 parameters, both double. Yeah, A and B. A is the base. B is the exponent. All right. What you call it, the syntax also pretty simple this way. Math, capital M. So why capital? Yeah, because this is a method in the static class. This math is a static class, static Java class. Do you know the concept of static class? What is the static class? Yeah. When you refer to a static class, you do not need to create an instance. Yeah. In Java, when you need to use certain method, you need to create an instance first, right? From a class. But that's for the non-static class. You need to create an instance. For static class, you just use the class name directly because it's static, right? Yeah. If you are not familiar with the static class concept, I can explain, if at some appropriate time, I can explain this concept. Yeah. Anyway, yeah, here we just use math.pow, then parenthesis a comma b. So you can find the answer. You can find the monomial, this monomial answer. Then you do the remaining multiplications, additions, so you can do the method number 2 in this way. Yeah. Here in Java. I believe if you use C++ or Python, you can find the similar power functions. Yeah. Similar power functions. Just use it. All right. Yeah. Yeah. All right. Yeah. Any question about the project at this point? Yeah. Yeah. If no question, I want to go to our next topic about a technique, repeated squaring technique. Why repeated squaring technique is related to this, our current topic. I'm discussing with you the current topic, because why power function can do much faster than the brute force. Do you want to know why the power function is much faster? Yeah, yeah, because it uses that repeated squaring technique. Yeah. That's the relationship. It uses the repeated squaring technique. That's the reason behind it. The internal implementation, yeah, using this repeated squaring technique. Yeah. Let me talk about the main idea of this repeated squaring technique. Yeah. All right. So here our goal, we want to calculate, or yeah, I just say evaluate a monomial. X to the kth power, right? Yeah, that's our goal. Yeah. How many multiplications do we need? Yeah. If we do not use any technique, we know the answer is k, right? Yeah. Yeah. Here we want to greatly reduce this k number. All right. Yeah. Using some smart trick. Yeah. All right. Yeah. Let me use a simple example here to illustrate this little trick. Yeah. Let us consider x to the 4th power. Let's calculate x to the 4th power. Yeah, sorry, here I need to update the number of multiplications k minus 1. The reason minus 1, because we do not multiply coefficient. No coefficient here. Because when we have a coefficient, we need to do another multiplication. So no coefficient, so we do one fewer multiplication, k minus 1. Yeah. All right, so here, x to the 4th, right? No coefficient. By the old method, based on our old method, it should be 3 multiplications, right? Yeah, 3 multiplications. Yeah. All right. Now, let me use the repeated squaring. Yeah. All right. First squaring operation. First squaring operation. Okay. X times x equals x squared. 1 multiplication. How about that? Our first multiplication. Then second squaring. Right? Yeah. X squared times x squared. All right. We already find x squared value. Why we just reuse it? Here we use the reuse idea. Right? Reuse the existing data idea. Here the idea is this, as simple as this idea. Yeah, very useful. Reuse the existing data. Do not reproduce it, right? You already have the data. Why you need to reproduce it? Why you need to use the redundant calculation to recalculate it, right? Save that part, redundant calculation. So here you only do one more multiplication, you get x to the 4th. Here you can see this step are not the multiplication. So the total combine 2 multiplications. How about that? 2 multiplications, not a 3, improved from 3 to 2, right? Yeah. Then we generalize this idea. Yeah. X to the 8th, okay? X to the 8th, if by our old method, we need a 7 multiplication, right? Old method. If by this repeated squaring, we just need to do 3rd squaring. How about that? Continue from x to the 4th, 3rd squaring operation. All right, yeah, 3rd squaring operation. X to the 4th times x to the 4th. One more multiplication, we get x to the 8th multiplication. All right, you can see number 7 is reduced to 3. How big it is, right? How big it is. Think about that. Yeah. Yeah. Let me try another one to impress you a little bit. X to the 16th, right? If we use the old method, we get 15 multiplications. If we use the new method, you just do another round squaring, right? X to the 8th times x to the 8th, another round multiplication, you get x to the 16th. So you reduce from 15 to 4, how big it is, right? The difference becomes bigger and bigger. How about this method? How about this method? All right, yeah. All right. Let me give you my last example of today, all right? Last, yeah, because we're near the end of the class, just a few minutes away. So let me give you a last example to impress you a little more. Yeah. Let's look at, I ask you to calculate x to the 1024th power. How about that? 1024th power, more than 1000. You're familiar with this number, right? 1024, I think everybody is familiar with this number. For a computer science student, everyone is familiar with this number. It is 2 to the 10th, right? 2 to the 10th, right? Yeah, think about our old solution. 8 equals 2 to the 3rd, 3, exponent number 3, the answer is 3, all right? 16 equals 2 to the 4th, right? The answer is 4, right? How about this? 1024, it corresponds to 2 to the 10th. What is the answer? Oh, if we use repeated squaring, how many multiplications do you need to find this monomial value? Is it 10? Is it 10? Yeah, 2 to the 10th. Yeah. Now you think about the huge difference. With repeated squaring, you reduce the number from 1024 to 10. Is that improvement huge? Think about that improvement. Is that huge? Right? How huge it is. Think about that, right? Yeah. That's the reason when you use the power function, why it is so fast. Why the power function is so fast? Because this technique is used. This repeated squaring technique is used. All right, yeah. Try to understand this repeated squaring technique. Yeah, because I will give you many such questions, either in the quiz, in your homework assignment, and in the tests. All possible. All right, all possible. All right, yeah, yeah. But in the when I give you future questions using repeated squaring, I may not give you k is the power of 2. Here, the question I give you here, k is the power of 2. If k is not a power of 2, then you can still use the repeated squaring to get the answer. Now, all right. So after today's class, when you go home, think about if k is not a power of 2. Yeah, how to use the repeated squaring. You still use repeated squaring to try to use the minimum number of multiplications to find the value of a monomial. That's the question I'd like you to think about. Try a little bit, yeah, because you will have a great chance to have that kind of questions, yeah, either in quiz 1 or homework number 1. Yeah. All right, yeah, that's it. That's how much I like to talk about in today's class. And we complete part C. Yeah. So next time we just start part D. Yeah.